Coastal erosion and coastal erosional issues happen along a shoreline where more sediment is removed from the beach than is added from the longshore currents that are trying to replenish the sand and sediment. We're going to look at a sample problem and figure out the rate of coastal erosion and how fast the shoreline has been receding, similar to what you would do in the lab in a typical intro geology classroom. So we have this map. We have point A, which is on the red line that represents the coastline in 1984, and we have point B that's on the coastline when the map is made. And let's say the map is made in the year 2004. So what we're going to do is we're going to use an equation for velocity, because we're looking at the rate that the shoreline moved. So we are going to figure out V, velocity, equals d over t. D is distance that we will get by measuring two different areas on the map, and then t is time, which is the period of time that is elapsed that we are interested in. So let's start by solving D for the equation. So first we need to measure A to B on the map with our ruler to see how many centimeters it is. So we take our ruler, we set it on the map, and again, your image might be a different size, so your numbers might be a little bit different. My image is much larger, so it's going to be a bit bigger in size. And with the ruler, can find that A to B on my figure is 6.5 centimeters. So we're going to write that down for solving for D, and again that goes on the top of the equation. The next thing that we need is to measure the scale in centimeters using our ruler. So we are going to measure the kilometers portion of the scale, which is the only scale on this map, all the way across to see how many centimeters that is. And I get 8.1. So we write that onto the bottom of the fraction that we have set up. So we have D equals 6.5 centimeters, which is the distance from A to B with our ruler, over 8.1 centimeters, which is the distance of the scale with our ruler. And the last thing that we need to do to solve for D is to multiply that fraction we set up by the number on the end of the scale, which is looking at how many kilometers did we measure with our ruler. And for this map, that is going to be 3. So we put that into our equation. And what we see when we're solving for distance is that the centimeters that we measured with our ruler are going to cancel out because one is on the top and one is on the bottom. So what you do in your calculator is you say 6.5 divided by 8.1 times 3, and the answer we get is 2.41 kilometers. So write that down. And we are going to put that up where V is also. Because remember, V equals D over T, so we figured out the distance. We can put that up here. Now we need to figure out the time. Again, the shoreline that was longer ago was from 1984. And I said, let's say this map was made in 2004. So to figure out the time that has elapsed, we take 2004 minus 1984 and write that for T, and when we do the subtraction we get 20 years, which we can then write in to our equation for V. So now we have done all the steps necessary to calculate the rate that the shoreline has receded. So in our calculator we take 2.41 divided by 20, and we find that the shoreline has receded at a rate of 0.1205 kilometers per year. So it sounds like a small number, but often the rate is giving in something like meters per year. So if we were to convert it to meters per year, we'd multiply that number times 1,000 meters per every 1 kilometer. This way we have a kilometer on the bottom, a kilometer on the top. They'll cancel, so our answer will be left in meters per year. And we'd be looking at about 120.5 meters per year. So you may have to do some unit conversions once you get your initial answer in kilometers per year. Could be meters per year, meters per day, centimeters per day, whatever it is for that unit conversion. But this is a sample problem of what you could likely expect to do in an intro geology lab on coastal erosion.